This is a re-recording of a live technical webinar. The re-recording is happening due to a video quality issue that we had. So I'm going to run you through the same presentation. The topic is seasonal variation of soil resistivity effects on earthing systems. Typically, when we run a webinar, there is some housekeeping rules, but also importantly, when you attend one of our live webinars, we will issue you with a certificate. We have lots of webinars throughout the year, purely technical. You can, if you visit luma/elec, you can sign up to get alerts and you can subscribe to our channel, and you can also register for the next events. In this presentation, I will be covering what is soil electrical resistivity. I'll talk about multi-layer soil modeling, the effects of soil resistivity on touch voltages, the effects. Then I'll talk about temperature correction of soil resistivity, how weather affects soil temperature. I'll provide the equations for calculating soil temperature. I'll also talk about soil moisture and its effect on electrical resistivity. And I'll show you how to consider seasonal variation and apply that correction to your electrical resistivity measurements. There'll be a number of calculation examples, 5 in total. The first 4 are about simple examples covering hot climates, and the second 2 covering cold climate, temperature effects, and rainfall and snowfall effects on soil resistivity. Then I'll run you through a real-world case study for a 132 kV substation, where from start to finish, we will look at considering soil temperature and rainfall and correcting the soil resistivity measurements. Finally, we'll draw some conclusions and provide some recommendations. Throughout a lot of the modeling or calculations have been performed using SafeGrid earthing software. SafeGrid is finite element-based earthing modeling analysis software for performing earthing designs. With SafeGrid, you can model grids of any size, custom grids in multi-layered soils. You can model below ground or above ground earthing systems. You can perform calculations at low frequencies or high frequencies in the frequency domain or the time domain, and the algorithms are fully optimized. You can obtain a free trial of that software by visiting our website elec.com. Soil electrical resistivity has a huge impact on earthing system performance. It's vital before performing a design that we undertake site testing of soil electrical resistivity, and we usually use the Wenner 4-point method to perform the tests. There are several factors that affect soil electrical resistivity, or soil resistivity for short. Those are moisture, the soil type, compactness, and mineral content. Importantly, soil resistivity goes down with a rise in temperature. Let's remember that. And soil resistivity also goes down with a rise in soil moisture content. Multi-layer soil modeling. This is a typical soil resistivity plot where we have plotted field measurements, those denoted by the crosses, on an XY plot, and we have fitted a model to those points in order to deduce a multi-layered equivalent soil resistivity model. The objective of the model is to closely match the measurements. Here are some further examples of some multi-layer soil models. You can see 3-layer models, 5-layer, 2-layer models, which are quite rare. 3, 4, 5 layers are quite common. Up to 7 layers is really recommended. It's not really necessary to have more than 7 layers. But after correction, having said that, after seasonal correction, it's possible to have more, and we'll see that. Soil resistivity effects on touch voltages. So there are two important points to make here, and we can see that it's evidenced by the table and the plot here. The plot is a surface voltage plot for quite a small 20 by 20 meter earthing system, buried earthing system. But the main points are that touch voltages near an earth grid primarily depend on the electrical resistivity of the top soil layers. However, on the other hand, earth grid resistance and also grid potential rise mainly depends on the deeper soil layers, the resistivity of the deeper soil layers. So that becomes, especially the first point, that touch voltages are greatly affected by the top soil layers, becomes very important when we consider seasonal correction of soil resistivity. Soil temperature versus electrical resistivity. I mentioned earlier that soil temperature has an effect on electrical resistivity, and we can see that in the plot here for a typical type. It's saturated sand gravel soil type, and we can see that along the x-axis we've got temperature, and along the y-axis we've got resistivity. So let's look above 0 degrees. As temperature increases, resistivity goes down. That's also the case below 0 degrees. Note that the freezing point of soil it's not 0, but it's just below 0 degrees. Now, as soon as the soil freezes, we see a very significant increase in resistivity of the soil. But there is an effect of temperature, both above freezing and below freezing, on resistivity. The weather affects soil temperature significantly. There are a number of heat transfer that occur at the ground surface, and those include conduction, convection, thermal radiation, and moisture evaporation. Note that soil temperature is closely linked to ambient air temperature. Here is the equation for calculating soil temperature with depth. We note here that the variables it depends upon include the annual variation or fluctuation of air temperature and also the annual average ground temperature, which is closely matched with the average annual air temperature. Here we've assumed that it's plus 1 degree. Soil thermal diffusivity is another input, and the time of early spring or the first day of spring, which is defined as the time of the year when the air temperature is increasing such that it reaches the same value as the average annual temperature. That's the definition of the first day of spring. So we need to have that as an input, as a number of days into this equation. And the output is soil temperature at a particular depth on a particular day. It's quite simple to apply this equation in a spreadsheet, and these are the sorts of outputs you can see. So at the top, you've got air temperature variation throughout the year over 365 days. Note that this is for a cold climate, or northern hemisphere, I should say, not a cold climate. This is where you have summer during the middle of the year, so in the northern hemisphere, and you have the colder times of the year at the start and the end. Now, soil temperature, the ground surface temperature closely follows air temperature. That's the green plot at the top. You can see that it closely matches. It's actually just 1 degree warmer. Now, if we go deeper into the soil at 1 meter depth, the soil temperature is lower than the air temperature, and there is also a time delay or a phase shift between the two temperature curves. They're actually sinusoids, and that's caused by the thermal inertia of the soil, this time delay. Now, as we go deeper, we go to 3 meters of depth, 5 meters of depth, and then 7.85, and I'll explain what that means. As we go deeper, we actually approach the annual average air temperature for that location. So deep soil, the temperature of deep soil approaches or is close to the annual average air temperature for a particular location. Now, these temperature effects or variations, they don't occur beyond a certain depth. That's what 7.85 is here in this plot, Z max. So beyond a certain depth, the variation stops. This plot is temperature on a particular day with depth. So we've got depth along the x-axis to Z max, and we've got soil temperature along the y-axis. So in the summertime, the shallow soil layers are at a higher temperature than the deep layers. And at all times of the year, all these curves converge to the average annual air temperature plus 1 degree. We've got winter on the plot, and we've got the intermediate seasons as well, or days of the year. Soil moisture also has a strong impact on electrical resistivity of soils. Water content strongly influences soil resistivity up to about 20% of saturation or moisture content. Rainfall and soil moisture that's caused by rainfall really ceases to have an effect beyond around about 1 meter in depth. So how do we consider seasonal variation in our soil electrical resistivity measurements? Well, the calculation steps here. First, obviously, we need to take the measurements, and we should take multiple sets of measurements. The calculation steps are as follows. We need to calculate multi-layer soil models from the measurements. We need to process the temperature and rainfall or snowfall data. Rainfall and snowfall data is optional. We need to calculate the effects of the soil temperature and moisture content on the soil resistivity for all days of the year. We do it for all days. And then we calculate what would be the worst day or the most conservative day. And then we need to correct our soil models for the worst day. So our measurements were taken on a particular day of the year that was not necessarily the worst day of the year. Almost guaranteed that it wasn't and never will be. So we need to apply the correction, and I'll show you how important it is with the examples coming up very soon. The data required is multiple sets of soil resistivity measurements. We need weather data, very easy to obtain from websites in almost every country. Soil type data or a geological report can help with obtaining the soil type. And an important assumption with seasonal correction of resistivity measurements is that the one soil type is assumed for all of the shallow layers, and this is very much a reasonable assumption because temperature and moisture only affects really the shallow layers. First, I'll cover 4 quite simple calculation examples so that we can understand the principles and the impacts of the correction particularly on touch voltages. So it's a 20 by 20 meter grid that we saw earlier. We will investigate both soil temperature and rainfall effects for both hot and cold climates. Now, traditionally, these seasonal of soil resistivity measurements it was thought that they were usually only needed to be applied to very cold climates, but that's not the case. There are very significant corrections to these measurements for hot climates too, and we're going to show this, especially when you're considering rainfall. So the first 2 examples are about hot climates, where first one is where we only consider air temperature effects. The second one is a hot climate where we consider both air temperature and rainfall. The third example is a cold climate where we consider air temperature only. And the last 4th example is a cold climate where we consider both air temperature and precipitation. So that could be rainfall and snowfall combined. Example 1, it's a hot climate, temperature effect only. So Soil type was assumed to be clay. It doesn't matter for this example what we assume. In our software, there are dozens of soil types that you can select from. It's a southern hemisphere location. In the top right-hand corner, you'll see a plot of air temperature and ground temperature, ground surface, ground depth at 1 meter. And it merely shows that at the start of the year, you've got a peak. So summertime is at the start of the year, hence it's a southern hemisphere location. And during the middle of the year, you've got a minimum in air and soil temperature. And there is, at 1 meter depth, we can see the time delay or the phase shift between the red and the blue plots in the top right-hand corner. Now, some data for this site. So average annual ground temperature is 19.45. To obtain that, we just need to find the average annual air temperature and add 1 degree. The yearly fluctuation of air temperature is quite small, 3.16 degrees. To find that, all we need to do is look at a year and find the minimum temperature and the maximum temperature and take the difference. It's quite small. That suggests to me that this location is quite a tropical location in the southern hemisphere around the equator, where air temperature doesn't vary too much during the year, or not much at all. The first day of spring was found to be the 1st of November at day 305. Remember, so we can see here the average air temperature would be 18.545. So if you look at the top right-hand plot, if we drew a line from 18.45 degrees right across to the right and around day 305, you can see that's the point where air temperature is above 18.45 or crosses that point. That's the first day of spring. Now, the day of the measurements. So we are saying that in this hypothetical example, the measurements were taken during the summer on the 5th of February, day 36. That's the first red dotted line on the left. And the worst day is in fact during the winter time. And that's been automatically worked out by some software calculations. And let's think about why. So if we're only considering effects on soil resistivity, remember that as increases, resistivity goes down. So in other words, when temperature goes down, resistivity goes up. So in this case, the winter time is in the middle of the year, and so we've got a minimum in temperature, therefore we've got a maximum in average resistivity. And you can see that by the dotted line, the minimum T and the maximum resistivity. Those points are corresponding. So the worst day of the year was during the winter time. That's when the resistivity values would be the highest. But we took measurements during the summertime, so we need to correct for that. Let's look at the calculation results. Let me explain the plots in the bottom left-hand corner. So the blue step plot, you can see the blue line, which is flat on the left-hand side. That is the uncorrected resistivity at the shallow soil layers. Those are at around, if we look at the table, the value is at around 23 ohm meters. Now, correspondingly, the green step plot is the corrected soil model. Those values are increased. You can see those values, the corrected model in the table. Those are increased above 23 to 28, 26, 49 in the shallow layers. And it may seem, but in fact, these what appear to be slight increases will have a significant increase or cause a significant increase in touch voltages, which is what we're concerned about for safety. And I'll show that very soon. Let's look at the same example, the same hot climate, same location, same grid, or same measurements, but let's consider temperature and rainfall. Now, what we've done is we've added rainfall data If we look at the data, we can see there are peaks at the start of the year and at the end of the year. So it actually rains much more during the summertime in this location because it's southern hemisphere. And in the middle of the year, we have the lowest rainfall. So in other words, during the middle of the year, we have the coldest climate or the coldest temperatures, which result in higher resistivity. We also have the lowest rainfall. So dry and cold soil has higher electrical resistivity. But in this case, in this example 2, we've taken measurements at a slightly different time, still in the summertime. It would be, for this location, it would always be worse to take measurements during the summertime. Now, often we can't help when we need to take the measurements, but we can always correct them. And that's what this presentation is about. So the worst was again during the winter because it's dry and it's cold. Let's look at the impact on the soil resistivity. So the original model was the same as before. The shallow layers, which are mostly affected by temperature and moisture, have a relatively low resistivity of around 23 ohm meters. But in fact, if we took the same measurements during wintertime, those would be much worse. And in the bottom left-hand corner, you can see the green versus the blue plot. So the green and the blue correspond, overlap each other beyond a certain depth, but at shallow depths, the resistivity of the shallow layers is much greater with the corrected model during the wintertime. So it would be more conservative and a good idea to do your earthing design using the corrected resistivity model. Let's look at the next example. It's a cold climate. We see here that the average annual ground temperature is quite a lot lower. It's almost 0, 3 degrees. You can see the temperature plot in the top right-hand corner versus the days. So we are in a northern hemisphere location and it's a cold climate. So we have a peak temperature or a higher temperature during the middle of the year when we have summer, and at the start and the end of the year we have winter. So cold temperatures. You can see that in the soil and the air, obviously, it go below 0 degrees at the start and the end of the year. The yearly fluctuation of air temperature is around 17 degrees. The first day of spring is the 19th of April. The day of the measurement was during summertime, a very nice time to take measurements. I would suggest that it's probably almost impossible to take measurements during the winter time. So they were taken during the summer. But the worst case, the worst day, is definitely during the winter time, because remember, resistivity goes way up when the soil is cold and especially when it freezes. So we can see the two plots on the right hand side, the measured day and the worst day, where the worst day has the highest average resistivity corresponding with the coldest temperatures. Let's look at the corrected soil model. So you can see the step plot on the left-hand side. There is a very big difference between the blue curve and the green step curve. Let's look at the table. The original model is the same. The shallow soil layers in red, you can see their resistivities. The effects are extending only up to less than 1 meter of depth, actually, that the soil is freezing. But the resistivity is 100 times greater. So touch voltages are obviously going to be much higher in this case. Finally, let's look at in the fourth example, which is the same location, northern hemisphere, cold climate, but we are going to add the effects of rain and snowfall. Now, these calculations are obviously actually quite difficult, but the data you need to enter is not. We need to obtain the rainfall and snowfall data. We see from that data that the highest rainfall is actually during the middle of the year, which is the summertime, and the highest snowfall, which makes total sense, occurs during the deep winter or the start and the end of the year. And if we apply the combined corrections, we still see that the worst day corresponds to the coldest temperatures, which is during the winter time when the soil freezes. Let's look at the corrected soil model. When we consider snowfall and rainfall, as well as we can see a further increase in soil electrical resistivity of the topsoil layers, and the effects extend deeper into the deeper soil layers as well. We can see that more layers are created, more layers are affected by this snow and the rain. In this case, particularly by the snowfall, because that corresponds to the worst day. Let's arrive at the touch voltage effects for that simple earthing system, 20 by 20 meters. If we apply the original soil model and the corrected soil model for all four examples to that earthing system, and we calculated touch voltages along a line. Starting on the left-hand side, we've got the two hot climate examples. So on the top left-hand corner, we're only considering temperature effects. On the then example 2 on the left, we are combining infra-hot climate, temperature, and rainfall effects. So we can see moderate increases, I think significant increases in touch voltages of 11% and 33% respectively. And then on the right-hand side, we've got the cold climates where the soil freezes, and we see extreme increases in prospective touch voltages for both of those examples. But really, we can see that temperature has the greatest effect on those results. Let's now look at a real-world example of an earthing design where we are applying this soil correction. So the example is a substation. It's actually a 132 kV substation that's installed in Sydney, Australia. The measurements were taken on the 15th of March 2024. That's during our autumn time. We are going to apply the effects of seasonal variation, temperature, and rainfall to the soil resistivity measurements that we've taken. We will choose an appropriate soil type from the geotechnical report that we have. We will determine the worst case soil model, and we will find the maximum touch voltages for the worst case. The data that's required to apply these seasonal variations is some weather data. We have a website in Australia where you can easily obtain any sort of weather data, historical weather data. We're going to need annual average air temperature. I'm going to show you how to obtain that and what to do with it. We'll need annual air temperature variation or fluctuation. We'll need annual monthly rainfall. We will choose or we'll determine soil thermal diffusivity based on the soil type. And we will decide on the first day of spring, which for this location is the 1st of October. So the average annual soil temperature, remember that's average air temperature plus 1 degree. So I just need to find the maximum per month for this particular location. In this case, I had several years of data. I have selected a particular year to use that for my annual average air temperature. I add 1 degree and I end up with the average annual soil temperature, which is 23.7 degrees. And I'll show you how to use that in the calculation very soon. The yearly fluctuation of air temperature, I simply needed to know the minimum temperature, and I took the average maximum. I subtracted the minimum, and I arrived at 23.6 degrees, which is the annual variation of air temperature for this location, which I also need for the calculation. Rainfall data, simply I had years of data for every month, and I have selected a mean set of yearly data representative of all of those years. However, you could select a year that had the lowest rainfall or somewhere or you could select every month that had the lowest rainfall and combine that to use for your calculations. That isn't an engineering judgment for you to make. How do we determine the soil type? There are several ways. You could go to a website that tells you the soil type for the region or location, and then you simply select the soil type based on that data. More accurate, it would be to use a geotechnical report and to look at cross-section of the soil. In this case, this is an example geotechnical report, and it shows that we've got silt as the topsoil layer. We've got some different types of clay as we go deeper, and then the digging or the report stops at 3 meters of depth, which is okay for us. In this example, I've selected silt as my soil type because I know that it has higher thermal diffusivity. That's actually more conservative. That means that the temperature effects or temperature variation will be seen at greater depth if I use a material or a soil type that has higher thermal diffusivity. So I've used silt instead of clay. So if I just consider soil temperature, this is our software on the left-hand side. I first need to select the soil type, and then I would enter those values that I've collected, such as the mean annual air temperature, the amplitude or yearly of air temperature, which I calculated from the minimum and the maximum, and then enter the first day of spring. That's simply it. I would enter my measurements, and I need to tell the software, you'll see in the bottom right-hand corner, the measurement date, the date that I took the measurements, and the software will actually calculate the model. It will correct the model for every single day of the year, and it will come back with the worst day and the worst model. Now, in this case, it's come back with an adjusted soil model. You can see that green step plot there. We actually end up with 11 soil layers. I believe this started with 5. We've added the corrected soil model includes an additional 6 soil layers in the shallow soil. So the difference, just considering temperature for this Sydney location, is quite significant. The soil model is quite different. The touch voltages will be quite different. Let's look at the model if we also consider moisture or rainfall. So we simply add our rainfall data. In this case, I've entered it as a spreadsheet, my monthly rainfall data, and then the software has, again, automatically calculated the worst day or the most conservative soil model on the worst day. Let's look at the final result, which is the impact of the different soil models on our touch voltages. So this is a reasonably large 132 kV substation, around 200 square meters, or 200 by 200, I should say. In the top left-hand corner, seasonal variation not being considered. So I've used the original soil measurements taken on the measurement day, which I believe was in March. And I've calculated prospective touch voltages, and I've come back with a maximum touch voltage of around 430 volts, quite a bit lower than the other cases. So if I applied or considered soil temperatures to the data, and I consider that, or I correct the data to be on the worst day for temperature alone, the actual maximum touch voltages would be much higher at around 730 volts. This is a very different case, a very different design that you need to deal with now. And on the bottom, if I consider both soil temperature variation and rainfall data, I've got very significantly higher prospective touch voltages in my calculations, which is very important to know about and to consider and to design for. There's another example here, which is a slightly larger earthing system, a more generic case, lower prospective touch voltages. So plot number 1 is without seasonal variation or correction. Plot number 2 is only temperature correction, higher touch voltages, quite a bit higher. And then the bottom plot, plot number 3, is where I've considered temperature and rainfall. Now I believe that this is a cold climate. So you've got a 300% increase in touch voltages. So in other words, it's very, very important to consider the effects of weather on your earthing systems. In conclusion, and finally, some recommendations. Annual soil temperature and moisture variations have a significant impact on soil electrical resistivity, especially for depths up to about 10 meters, so the shallow soil layers. It's very unlikely that you measured soil resistivity at the worst time of the year, and this must be checked. The resistivity of shallow layers could be much higher than expected. Touch voltages for earthing systems are greatly affected by the resistivity of the shallow soil layers, and touch voltages could be much higher than expected. Finally, recommendations. Always apply seasonal correction to soil electrical resistivity measurements. This includes for both dry climates or cold climates where the soil freezes, both types of climates. Thank you so much for watching. If you have any questions, you can reach out to me personally. I look very much forward to seeing you on one of our next technical webinars. Thank you again for your time.